Good afternoon, everyone. Let's wait for 5 minutes so that other people can also join. Okay, so let us continue with the problem that we left in the previous session. I'll just recall the problem statement. Question number one. Let an be a sequence of real numbers. Now define a sequence Sn, the sequence Sn by following. Sn is equal to 1 by n summation I from 1 to NAI, which is basically A1 plus A2 and so on up to AN upon n. We are just taking some average of the first n terms. I'm sorry for the interruption. Let's start again. Let an be a sequence of real numbers, and we define a sequence Sn, which is 1 by n summation I from 1 to n ai. So basically we are just taking average of first n terms of the sequence an. First part says that if an is monotone and bounded, then show that the sequence Sn is also monotone and bounded. This part we had already done in the previous clip. Oh, I don't know what's happening. Let me use notes again. I guess there is some issue with the OneNote. Okay, I'll just write it again. We have a sequence of real numbers an, and using this an, we define the sequence Sn summation I from 1 to n ai 1 by n. And the first part said that if an is monotone and bounded, then that would imply the same for the sequence Sn. Sn is monotone and bounded as well. This part we had already done in the previous session. Next part says that if the sequence an converges to some limit, if the sequence an is convergent and it is converging to a, then show that the sequence asn, show that Sn also converges to A. Let us see how. Proof of the second part. So let's see how Sn minus A looks like. So now mod Sn minus A, this is by definition of the sequence Sn, this is just A1 plus A2 and so on up to An upon n minus A, which is mod A1 plus A2 and so on up to an minus n times a upon n. Now I can split this n times a as a plus a n times. So this is modulus a1 minus a plus a2 minus a and so on up to an minus a upon n. Now using triangles inequality, this is less than equal to 1 by n times mod a1 minus a and so on up to mod an minus a. Let's mark this equation as 1. Now we'll use the fact that the sequence an is converging to a. So now since an converges to a, this is the notation how we write a sequence converging to some point a. By definition, for any epsilon positive, again we'll be able to get a stage n naught. There exists some n naught in n such that this mod an minus a will be less than epsilon for all n greater than equal to n naught. Now if I take the constant alpha to be the maximum of mod a1 minus a, mod a2 minus a, and so on up to mod a capital N naught minus 1 minus a. Now since this capital N naught is a fixed term, these are fixed n naught minus 1 terms. So obviously we can find maximum of finite number of terms. So this maximum is well defined. And therefore, for n greater than equal to n naught, by above equation 1, we have mod Sn minus a less than equal to. Now see, first term is mod a1 minus a, which is the term here also. That means alpha is greater than equal to mod a naught minus a1 minus a, and so on. Somewhere in between, we must have got some term of the type mod a n naught minus 1 minus a. So up till there, all the terms will be lesser than alpha. So this turns out to be less than equal to alpha by n plus alpha by n and so on up to alpha by n. These are first n capital N naught minus 1 terms, and after that we have summation k from n naught to small n, because we had this sum up till small n and small n is greater than n naught, so obviously we will be having some extra terms. So this is mod a k minus a upon n. Now this is n naught minus 1 times alpha by n plus summation k from n naught to n mod a k minus a upon n. Now the subscript here, see the subscript here, this k is greater than equal to n naught. And we know that if I mark this as equation 2, So by equation 2, for the subscript greater than equal to n naught, here we have this k greater than equal to n naught, this mod an minus a is less than epsilon. So this will be strictly less than n naught minus 1 times alpha by n, and all these terms will be lesser than epsilon, and 1 by n will be as it is, because since by equation 2 mod ak minus a is less than epsilon for all k equal to n naught plus 1, and so on up till n. Okay, so this is just sum of terms, same terms. Basically, this is epsilon by n, and so on, n naught minus n times. So this becomes n naught minus 1 times alpha by n plus this will be epsilon by n minus n naught minus 1. So this is not n naught minus n times, because we are starting from n naught to capital N. So this will be n minus n naught minus 1. And this is less than equal to n naught minus 1 alpha by n plus epsilon by 2. Now this is because we have capital N naught greater than equal to 1, which gives us n naught minus 1 minus n greater than equal to minus n, which gives us n small n, sorry. So this will be n minus n naught minus 1. So basically multiplying by minus 1. So the inequality will interchange, less than equal to n. So n minus n naught minus 1 by n will be less than equal to 1. So multiplying it by epsilon, n naught minus 1 by n, this will be less than equal to epsilon. Okay, this is less than epsilon. This should be okay. Now by Archimedean property, we can find a natural number capital N1 such that this is just a real number, n naught minus 1 times alpha. This will be strictly less than n epsilon by 2 for every n greater than equal to n1. So that will give us mod. In fact, yeah, Sn minus a is less than epsilon by 2. This epsilon for all n greater than equal to maximum of n naught n1. So this is mod Sn minus a less than, this will be 3 epsilon by 2, or instead of epsilon, I can take 2 by 3 times epsilon. For all n greater than equal to, I will take this as n2, taking epsilon dash to be 3 epsilon by 2, because any epsilon dash can be written in the form of 3 epsilon by 2, because epsilon was arbitrary. So from here we get mod Sn minus a is less than epsilon, or epsilon dash, for every n greater than equal to n2, and where this epsilon dash positive is 0. So this will be mod Sn minus a less than epsilon by 2 is less than epsilon dash for every n greater than equal to n2, and where this epsilon dash positive is 0. So this will be mod Sn minus a less than epsilon by 2 is less than epsilon dash for every n greater than equal to n2, and where this epsilon dash positive is 0. arbitrary. Since any epsilon dash positive can be written as epsilon dash is equal to 3 by 2 times epsilon. For some real number epsilon, obviously we can always find such an epsilon. And this gives us the definition of convergence of the sequence. Therefore, the sequence Sn converges to A. I hope this is clear how the sequence is converging to A. If you have any doubt, you can ask. Okay, then, if there's no doubt, let's move to the next question. Question number 2. If we have a positive real number a1 and we define the sequence an such that an plus 1 is given by 1 by 2 times an plus 2 upon an. Here each term is governed by the previous term. So basically, in order to find any term of the sequence, we need to know what was the term before it. So such sequences are called the recursive sequences. And this is happening for every n greater than equal to 1. Then show that that the sequence an n greater than equal to 2 is non-increasing and bounded. Also, we know that monotone and bounded sequence is convergent, so eventually it will be convergent. So they're asking us to find its limit as well. Also, find its limit. Solution. Now, firstly, we'll see whether the sequence is non-increasing or not. For that, we need to see the behavior of the terms an plus 1 minus an, whether it is positive or negative or how it is changing. So now this an plus 1 minus an, this is equal to, by definition, this is 1 by 2, an plus 2 by an, and I will take this an as it is. So taking LCM and all, you'll eventually get this is equal to 2 minus an square by 2an. Now here we can see that the term an plus 1 minus an, in order to show that the sequence is non-increasing, so basically decreasing, we want this to be less than equal to 0. Now this will be less than equal to 0 if and only if 2 minus an square is less than equal to 0. Because obviously a1 is positive. By the definition of the sequence an, we can see that a2 will also be positive. All the terms will be eventually positive. So this denominator term is always positive. So in order to get this whole to be negative, we should get 2 minus an squared to be negative, less than equal to 0. That means the sequence an is non-increasing or decreasing if and only if, this is the symbol for if and only if, an square is greater than equal to 2. For all n, we need to show that the sequence is non-increasing for all n greater than equal to 2. So we want this to be for all n greater than equal to 2. Now this happens for since an's are all positive, so this will happen if and only if an is greater than equal to root 2 for all n greater than equal to 2. Now we claim that, let us claim that this an is greater than equal to root 2. Then only we'll be able to prove that the sequence is non-increasing. Now let us see what happens if an is greater than equal to root 2. Now we have an greater than equal to root 2 if and only if, by the definition of the sequence, this will be 1 by 2 an minus 1 plus 2 by an minus 1. This is greater than equal to root for all n greater than equal to 2. Now this will happen if and only if, taking the LCM and all, you'll get an minus 1 square plus 2 upon 2 an minus 1. This is greater than equal to root. Now since again an minus 1, all the terms of the sequence are positive, I can just multiply both sides with 2 an minus 1. So this will be an minus 1 square plus 2 greater than equal to 2 root 2 an minus 1, and this is happening for all n greater than equal to 2. This eventually gives us a quadratic equation, plus 2 minus 2 root 2 an minus 1 greater than equal to 0 for every n greater than equal to 2. Now here we can see that this is nothing but the expansion of an minus 1 minus root 2 whole square. Now what does this symbol if and only if means? This says that both the conditions occur at the same time. But basically this gives us an is greater than equal to root 2 for every n greater than equal to 2 if and only if an minus 1 minus root 2 square is greater than equal to 0 for every n greater than equal to 2. So let me just clarify what do we mean by this if and only if statement. It says that suppose P is some statement and we are saying that P if and only if Q. That means if P holds, if P is true, then Q must also be true. Q must also be true. And at the same time, if Q holds, then P must be true. That means both these statements occur simultaneously. Now we all know that this is always positive because this is a square of some real number. We know that square is always positive. Now since an minus 1 minus root 2 square, this is positive always, this implies an greater than equal to root 2 for every n greater than equal to 2. And hence, so we can mark this as equation 1. Therefore, by equation 1, now since we have given again an greater than equal to root 2 if and only if the sequence is increasing, is non-increasing, both the statements should occur simultaneously. Now since we have proved that an is greater than equal to root 2, therefore by equation 1, the sequence an is non-increasing. Next we need to see whether the sequence is bounded or not. For that, next we claim that the sequence an is bounded. Now since we are given that our sequence is non-increasing, that means basically decreasing. So this gives us, since an, this is for n greater than equal to 2, n greater than equal to 2 is non-increasing, This tells us that A2 is greater than equal to A3, greater than equal to A4, and so on. So that means the upper bound for our sequence is, can anyone tell me what will be the upper bound for our sequence? You can just write in the chat or unmute yourself. So since all the terms of the sequence are lesser than equal to A2, the upper bound, not infinity, upper bound. The upper bound is the term, a real number such that all the elements in the set are lesser than equal to that number. So we can see that if we consider the set S to be an, n, 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 this is nothing but the collection of the sequence n greater than equal to 2. N greater than equal to 2. So this is just the collection of the terms in the sequence. We know that all the terms are less than equal to A2. Yeah. Therefore, uh, upper bound for S, upper bound for S will be A2. When do we say a sequence, a set is bounded? We say a set is bounded when it has both upper as well as lower bound. So clearly we got the upper bound. Also, we have a lower bound. If you can see what we did previously, it is actually, I have written it in this page only. You can see it directly. Can you tell me what will be the lower bound of the set S? So lower bound is basically the real number alpha such that all the terms of the set are greater than that alpha. We had just proved something. In order to prove that the sequence was non-increasing, we proved that an is, we proved that an is greater than equal to root 2. That means all the terms are greater than equal to root 2 in S. That means root 2 is a lower bound. And since an is greater than equal to root 2, for every n greater than equal to 2, means lower bound for S will be root 2. Therefore, the set S or the sequence an, the sequence an, n greater than equal to root 2, sorry, just 2, n greater than equal to 2, this is bounded. That's what we need to prove. We until now we have proved that the sequence is non-increasing, so basically it is decreasing and bounded. So let me just recall a result that you must have done in your theory lectures, that any monotone and bounded sequence is always convergent. A monotone and bounded sequence is convergent. And in fact, if we have, if the sequence X, suppose an is increasing and bounded above. So one can notice that what happens in this case, we have a sequence which is increasing. That means suppose this is 1, 2, 3, and so on. If we plot that function corresponding to the sequence, we know that sequence an can be written as a function from the set of natural numbers to the set of real numbers R. So this plot will be an increasing graph. And we are saying that it is bounded above as well. That means none of the terms will pass this line. So eventually what will happen? A lot of terms will be together, will lie some point, which will be obviously lesser than the this upper bound. So eventually the sequence turns out to be convergent. An is convergent. Similarly, if the sequence an is decreasing and bounded below, then also we get this that the sequence is convergent. So this is a very good result. You all must be well aware of this result. So for our above given sequence an, firstly we had shown that it is a non-increasing. So basically it is a decreasing sequence, and it has a lower bound also. It is bounded from both sides. So eventually it is monotone and bounded sequence. Hence it is convergent. Now, since an n greater than equal to 2 is monotone and bounded, yeah, Cauchy if and only if convergent is true when we are talking about the sequence of real numbers. It might not be true always, but as far as I know, you all are going through this course of real analysis, so you should not be confused. Always a sequence is Cauchy if and only if it is convergent. In some other spaces, it happens that the sequence might not be convergent even if it is Cauchy. Monotone and bounded. Okay. Therefore, the sequence is convergent. Now the question is asking us to find the limit. Suppose it converges to some L. Suppose limit n tending to infinity a n is L. So by definition, this now since we have a n plus 1 is equal to 1 by 2, a n plus 1 by a n is 1 by 2 by. So taking limit both the sides and using the algebra of limits, we get L, because a n plus 1 is again the same sequence, it is converging to L. This will converge to L plus 2 by. So this eventually will give us a quadratic equation. So this will give us 2L square minus L will be 0. So basically this is, yeah, L square, no? Yeah, L square. So this is L square minus 2 is equal to 0. L is equal to plus minus root 2. Now, since all the terms of the sequence are positive, so this sequence can never go towards minus root 2. Since n is greater than equal to 0 for every n in n, therefore L will be root 2. The case of minus L equals to minus root 2 gets discarded. Therefore, if the sequence is convergent and it is converging to root. I hope this solution was fine with everyone. If you have any doubt at any step in this problem, please let me know. I can repeat it. This is a very important sequence. You all should know that this converges to root 2. In fact, using this, yeah, we can make a so basically, this is a sequence. If I take a1 to be some rational number, we can eventually get a sequence of rationals which are converging to root 2, which is irrational. So this is also a way of constructing a sequence of rationals which are converging to irrationals. And yeah, this is a very good example. Okay, then let's move to next question. So yeah, prove or disprove that the sequence summation k from 0 to n. So I define this xn to be summation k from 0 to n, 1 upon k plus n square. Now we are saying that it converges to 0. We need to see whether this is true or false. Now for that, firstly let us see how does the terms of the sequence xn looks like. Solution. So this xn, this is taking k equals to 0, this will be 1 by n square plus 1 by n plus 1 square, 1 by n plus 2 square, and so on up till 1 by 2n square. So in order to prove that this sequence is actually convergent, we'll be using the sandwich theorem or the squeeze theorem. So let me just recall, what do we mean by squeeze theorem? I think you must have done this in theory class. So if we have three sequences, if xn, yn, and zn are sequences of real numbers, such that one of the sequence is squeezed in between the other two. So basically such that xn less than equal to yn less than equal to zn for all n in n, and the sequences in between which the sequence yn is squeezed, both are converging to the same limit, and limit n tending to infinity xn is equal to limit n tending to infinity zn. If such condition holds, then the sequence yn must also converge to the same limit. That means if we have a sandwich, suppose bread, and in between we have some, we can say the patties. So if this both the breads are converging to the same limit, so the in between one must also converge to the same limit. So that is why sometimes we call it sandwich theorem or squeeze theorem. Then limit n tending to infinity xn is equal to limit n tending to infinity yn equal to limit n tending to infinity zn. Now we'll be using this theorem in order to show that the above sequence is actually converging to 0. So so for that, fx equals to sin x is given as injective. Yeah, I think that is some error in that question. Even I saw that, because sin x is never injective. In fact, sin x is a periodic function. No? After period 2 pi, the terms will always have the same value. So yeah, even I don't think it will be injective. Okay, so we had xn is equal to 1 by n square plus 1 by n plus 1 square, and so on up to 1 by n plus n square. So we will find sequences yn and zn such that this sequence xn is in between both these sequences. So for that, we'll use the fact that since n square is less than equal to n plus k square for every k positive, obviously n plus k is greater than n, and taking square will eventually give us the same inequality. So now taking reciprocal, we know that the inequality will interchange on n plus k square. So this will give us xn, this happens for every k greater than equal to 0, which was 1 by n square plus 1 by n plus 1 square, and so on up to 1 by n plus n square. This will be less than equal to 1 by n square plus 1 by n square, and so on up to 1 by n square. So this is n times 1 by n square, so which is 1 by n. So from here we got an upper bound. Let the sequence Zn be 1 by n for every n in n. So from here we get xn is less than equal to Zn for every n in n. Let's mark this as equation 1. Next we will look for a sequence which is lesser than equal to xn. For that, now since n plus k is less than equal to n plus n for all k, see, we are taking k from 0 to n, na? So for all k 0, 1, 2 up till a n, k is always less than equal to n, so n plus k is less than equal to n plus n, so that will give us 1 upon n plus k square. The inequality will interchange, greater than equal to 1 by 2n square. This is happening for every k 0, 1 to n. Now this will imply xn, which was 1 by n square, 1 by n plus 1 square, and so on up till 1 by n plus n square. This will be greater than equal to 1 by 2n square plus 1 by 2n square, and so on up till 1 by 2n square. So this is basically again n times 1 by 2n square, which is 1 by 4n square. No, just n. Yeah, n and n square will get cancelled out. So let yn be equal to 1 by 4n for every n in n. We get xn is greater than equal to yn. Also, and limit, we all know that the sequence 1 by n converges to 0. Here, again 1 by 4n will also converge to 0. So if I mark this as 2, so by first and second, we get yn less than equal to xn less than equal to zn for every n in n, with limit n tending to infinity, yn is equal to 0, which is equal to limit n tending to infinity zn. Therefore, by squeeze theorem, the sequence xn converges to the same limit, which is 0. Therefore, the given statement was true, and the sequence xn must converge to 0. So the main idea was to use this sandwich theorem or the squeeze theorem and see what will be the upper and lower sequences, Zn and Y. I hope this is fine with everyone. If you have any doubt, you can please ask at any step. Okay, then let's move to next question. Oh, check if the following sequences are Cauchy or not. Following sequence. Check if the following sequence is Cauchy or not. And the sequence is an is equal to summation k from 1 to n 1 by k factorial. So basically each term is just 1 by 1, 1 by 2 factorial, 1 by 3 factorial, and so on up to 1 by n factorial. We need to see whether this sequence is Cauchy or not. For that, let us firstly recall the definition for Cauchy sequence. The sequence an is called Cauchy sequence if for any epsilon positive there exists a stage such that after that stage, earlier for the convergence, we used to see whether all the terms are near to some fixed point L. And for Cauchy, we need to see that after some stage, all the terms are near to each other. There is a very slight difference. In fact, in the case of real numbers, there is no difference at all. Saying it is a Cauchy is equivalent to saying that it is convergent, but in several other spaces it happens that the sequence might be Cauchy. That means the terms of the sequences might be near to each other, but still they not converge. So this such that xn minus xm, so any two terms, the difference between any two terms is less than epsilon for all n m greater than equal to n. So after a stage, all the terms are very much near to each other. That's what we mean by Cauchy sequence. So now we'll see whether the above given sequence is Cauchy or not. Solution. So yeah, for that, oh, this is write it as xn. So for that, we need to check how does this mod an minus am look like. So by definition, this is summation k from 1 to n, 1 by k factorial minus summation k from 1 to m, 1 by k factorial. So the initial terms will be actually the same. So they'll get cancelled out. So eventually this will be just summation k from yeah, we should start with the suppose m is less than equal to n. We can take n less than equal to m as well, just for yeah, obviously if we have two distinct natural numbers, one of them will be lesser than the other one. This will be so eventually this will be k from m plus 1 to n 1 by k factorial. Now since I'm saying that this will be less than equal to summation k from m plus 1 to n 1 upon 2 to the power k minus 1. That is because k factorial is always greater than equal to 2 to the power k minus 1 for every natural number. You can easily, I think you must have proved it in your PMI course. Yeah, using PMI, you can prove this. This happens for every k in n. So yeah, when we take the reciprocal, the inequalities get interchanged. So eventually 1 by k factorial is less than equal to 1 by 2 to the power k minus 1 for every natural number. And this is nothing but a geometric progression. So this is 2 to the power m, 1 upon 2 to the power m plus 1, and so on up till 1 upon 2 to the power n minus 1. So taking 1 by 2 to the power m common, this is 1 plus 1 upon 2 to the power m plus 1. So on up to 1 upon 2 to the power. This will be n minus m minus 1. And this will be obviously less than equal to the infinite sum because these are positive, all the terms in the series are positive. So this will be less than equal to 1 upon 2 to the power m summation k from 0 to infinity 1 by 2 to the power k. Now we know that this is an infinite GP, infinite geometric progression, and this is equal to 1 upon 1 minus 1 by 2. So this will eventually be, we all know that when we have summation, suppose r from 0 to infinity, sorry, this will be n, n from 0 to infinity, 1 up, some r to the power n, where this r is strictly less than 1 greater than 0. This is an infinite geometric progression, which the sum eventually gives, this is equal to 1 upon 1 minus r. So this will be 1 by 2 to the power m times 1 upon 1 minus 1 by 2 will be actually equal to 2. So this implies mod an minus am. This is less than equal to 2 upon 2 to the power n. Now, by Archimedean property, for any epsilon positive, by Archimedean property, for any epsilon positive, we can find some natural number n naught such that 2 by 2 to the power m will be less than epsilon for all m greater than equal to n. So that's the beauty of the Archimedean property, which would eventually imply that mod an minus am, this is strictly less than epsilon for all m greater than equal to n naught. Now, since n was already greater than equal to m naught, and since n greater than equal to m, this will be greater than equal to m naught. So I can write it as mod an minus am is less than epsilon for all n and m greater than equal to n. This gives us the definition of Cauchy. Therefore, the sequence an is Cauchy. I hope this is clear how we prove that this sequence is a Cauchy sequence. I would like you to go through it once again. Yeah, I'll come back in 2 minutes. Next, we'll look at series. Before that, I would like to recall what do we mean by series, convergent series. Okay. So I hope till now there is no doubt. We'll just move ahead. Hmm. Um, am I not audible?
Now you're audible, ma'am. That was my mistake,
Okay, okay, okay.
my network issues.
Huh. So series, we generally write it as something like this, where an is some sequence. So we start with a sequence. Suppose an is some sequence, is a sequence of real numbers. Using this sequence, we construct another sequence Sn. So with whose terms are S1 is equal to A1, S2 is sum of first two terms, S3 is sum of first three terms, and so on. So the nth term of the sequence Sn is just the sum of first n terms of the sequence An. Now we say this sequence Sn, the sequence is called the sequence of partial sums. Sequence of partial sums. We can see that as n tending to infinity, this Sn will eventually be the infinite sum of the terms of the sequence an, which looks something like this. So we say uh, the series, we say the series um, mm, hmm. We say that this infinite sum or the series summation n from 1 to infinity is convergent if and only if this sequence Sn is convergent. So series is actually nothing new term. Series is again a sequence. Convergence and divergence of a series is again depending on the convergence and divergence of a sequence. Now, but the only thing is that this sequence is of a special kind. It is basically the sequence of partial sums, and which is constructed using another sequence A if and only if Sn is convergent. So we should not get afraid when we hear the term series. Series is nothing but the sequence of partial sums. So we have some results. I would like to recall all those results that we will be using in order to prove whether the series is convergent or not. Uh, okay, we have some results. I would like you to note these results so that for the future purpose, I'll be just saying some by this test, we are saying that the series is convergent. So you must be aware that what do we mean by those tests. Though, so the first result says that we call it the Cauchy condensation test. Cauchy condensation test. It says that suppose an is a sequence, an is a decreasing sequence. be a decreasing sequence of positive real numbers. An is a sequence whose each term is positive and the sequence is decreasing. Decreasing sequence of positive real numbers. Then the summation n from 1 to infinity converges. The series converges if and only if the series summation n from 1 to infinity 2 to the power n a 2 to the power n is converges. We will be using these results. You'll see how this actually work. Converges. Okay, so we call this as Cauchy condensation test. Next, we have a theorem, which is a very basic and important theorem, which says that if the series summation n from 1 to infinity converges, then we can say something about the sequence an as well. If we are given that a series is convergent, this is summation an, so that would directly imply that the sequence an is converging to 0, or limit n tending to infinity an is 0. I hope the proof of all these and the theory behind all these things will be done in the class. So I won't be doing that. If you want me to discuss the proofs also, you can let me know. I'll discuss it in next session. Then we have comparison test. Comparison test. It says that suppose an and bn be sequences of positive real numbers such that an is less than equal to bn for every n, then we have the following. If the lower sequence, if the bigger sequence converges, the if the bigger one is if the bigger series is convergent, so basically if summation bn n from 1 to infinity converges, then the lower one must also converge. This implies summation n from 1 to infinity an converges. And if the lower one, if the smaller one, whether we should say the smaller one, if the smaller one is divergent, then the larger one will eventually be also divergent. If summation n from 1 to infinity an diverges, diverges means the sequence of partial sums is divergent, it is tending to infinity. Obviously, because an and bn all are positive terms, so this sequence Sn will be a1, a2, and so on, the sum of positive real numbers. So when we are saying that the sequence Sn is not converging or the sequence Sn is diverging, so that means it is eventually going to infinity. Diverges. This implies the sequence, the larger one. Obviously, if the smaller one is going to infinity, the larger one will be going to something larger than that, which is again infinity. Summation n from 1 to infinity bn diverges. Okay. Then we have P series test. Number 4. P series test, which basically says that summation n from 1 to infinity 1 by n to the power p. This is convergent for all p strictly greater than 1 and divergent for all p less than equal to 1. Then we have ratio test. Which says that if summation an is a series, suppose summation an and from 1 to infinity be a series in R, and we let A to be lim inf. I hope you all must be aware with the term of lim inf, limit inferior of the sequence mod an plus 1 upon an, and capital A is the lim sup, limit superior. Are you familiar with these terms, limit superior, limit inferior?
Yes, ma'am.
Okay. Then we have the following summation an, or instead I should write it as, now if capital A is less than 1, then summation an converges absolutely. Absolutely means summation mod an is convergent. So this is the notation for saying that the series is convergent. Second point says that now if small a is greater than 1, then summation mod an diverges. Else, in any other case, the test fails. That means we do not know what happens. Else, the test fails. Similarly, somewhat similar kind of result we have that we call the limit comparison test. Here, instead of an plus 1 and an, we have an and bn. Let's see how. Limit comparison test. Now, if we have two sequences, let an and bn be two positive sequences, all terms are positive, then firstly, if limit n tending to infinity, an by bn is equal to some finite real number c, and this is strictly positive, then both the series summation an and summation bn converges and diverges together. That means if either one of them is convergent, then the other one will also be convergent. If either one of them is divergent, then the other one must also be divergent. Then summation an and summation bn converges or diverges together if this limit is a finite positive real number. Next, if this limit is 0, in that case, we say that if summation bn converges, then summation an converges. not the other way around. If the denominator term, the series corresponding to the denominator is convergent, then the series corresponding to the numerator will also be convergent. And next is the case when this limit is infinity. We have somewhat opposite result, which says that if summation bn diverges, if the denominator one is diverging, then the numerator one will also diverge. Then we have root test. Don't worry, we'll be using these tests. You'll see how these tests are useful. I just wanted to recall everything here so that in further lectures I will not have to write them again and again. If we take a to be limit superior of this sequence mod an to the power 1 by n, then firstly we have summation an. Okay, let's write if this a is strictly less than 1, then summation an converges absolutely. That means summation mod an converges. Then we have a greater than 1. If a is strictly greater than 1, then the summation an diverges. And for the case of a equals to 1, we don't know anything. Test fails. Okay, yeah, one more result. You can write it as a theorem, which says that if an is a sequence such that it is decreasing, an plus 1 is less than equal to an for every n and n, and it is converging to 0, then the series summation n from 1 to infinity minus 1 to the power n times an, this is finite. This series converges. Okay, so let's see how we will be using these results. Let's move on to some problems. So we did till question number. Again, I guess everything went back. Okay, it's fine. The question says that if the sequence an is a positive, non-increasing sequence, that means we are in the setup of the Cauchy condensation test, and summation an is convergent, prove that limit n tending to infinity 2 to the power n, a 2 to the power n is 0. Just recall the Cauchy condensation test. I can't because I don't know how everything went back. So yeah, what does Cauchy condensation test says? It says that if the sequence an is positive, non-increasing, then summation an converges if and only if summation 2 to the power a 2 to the power n convergent. Now we are already given that summation an is convergent. We are already given in the problem that summation an is convergent. Since summation an is convergent, that means by Cauchy condensation test, summation 2 to the power n, a2 to the power n is convergent. N from to infinity. Next, we also had a theorem that says that if a series is convergent, the sequence corresponding to that series converges to 0. That means this implies the sequence 2 to the power n, a2 to the power n converges to 0. That's what we need to show. I hope this is clear. How we used the Cauchy condensation test. So mainly, yeah, we use the Cauchy condensation test and the fact that the sequence corresponding to the convergent series converges to 0. Okay. Next, we'll have, if suppose we have a sequence an such that 0 less than equal to an less than equal to 1 for every n in n, and we have a real number x which lies in between 0 and 1. Prove that summation an x to the power n and from 1 to infinity converges. I would like you to try this yourself first. I'll give you a hint that you need to use the fact that this infinite GP, infinite geometric progression, is convergent, and then use the comparison test. Please try it. I'll wait for 5 minutes. Otherwise, there's no use of just me writing all the time. Sorry. So any idea? Now, since we are given that an is always less than equal to 1, that would give us, if we multiply x by an, this will be less than equal to x. So x to the power n for every n in n. Now, these are two sequences such that if I take this as, suppose Zn, and this one as Yn, the series summation Yn, n from 1 to infinity, is nothing but a geometric progression, because all the terms are just x, 1, sorry, x square, x cube, and so on, with x being strictly less than 1. So this is finite, because we all know that infinite geometric progression is convergent. Infinite geometric progression is convergent for, if the ratio, if the ratio, and in this case the ratio is x, is strictly less than 1, strictly greater than 0. So yeah, this should be actually strictly greater than 0. Yeah, also for equal to 0, this is just the sum, zero sum. So in that case, we don't need to worry at all. Yeah. Now, since the larger one, the series corresponding to the larger sequence is convergent by comparison test, if you just look back into your notes, if you had made notes, so by comparison test, the series summation Zn is convergent, or summation an x to the power n converges. That's what we needed to show. I hope this is fine. Okay, let's move to next question. We have, just test the convergence of the following series. Mm, summation n from 2 to infinity, 1 upon n log n to the power p. So can anyone tell me why did I take n from 2 to infinity? What was the problem with n equals to 1? So what happens at n equals to 1 here? Am I audible? And the second part is summation n from 2 to infinity, 1 upon log n to the power x. Here n equals to 1 gives us log 1 in the denominator, and we know that log 1 is 0. So that's kind of not defined. That's why we take some sum from n equals to 2 to infinity. So let's see. And here this x, yeah, for x being any way. Okay. Firstly, let's see the case where p is greater than equal to 0. Case 1 where p is greater than equal to 0. So we have an, this is equal to 1 upon n log n to the power p. Obviously, for all natural number, for all n greater than equal to 2, so we know that log x is positive for x greater than equal to 2. So this will eventually be greater than 0 for all n greater than equal to 2. Now, since n plus 1 times log n plus 1 to the power p, this is greater than equal to n times log n plus 1 to the power p. That's because n plus 1 is greater than equal to n. No? We are just multiplying it with some positive real number. And this will be, no, I'll write it. Since n plus 1 is greater than equal to n, and this will be greater than equal to n times log n to the power p. That's because log x is an increasing function. This log n plus 1 is greater than equal to log n. And again, taking power p also is an increasing function. So this will be greater than equal to log n to the power p. And yeah, next we just multiply it by n. So this gives us a n plus 1, which is equal to 1 upon n plus 1 log n plus 1 to the power p. This will be less than equal to, because while taking reciprocal, the inequality interchanges. This is less than equal to 1 by n log n to the power p, which is a. That means our sequence an is a decreasing sequence. Therefore, an is a sequence of positive real numbers and it is decreasing. So we are something in the terms of Cauchy condensation test. We have a decreasing sequence of positive real numbers. So by Cauchy condensation test, the series summation an will converge if and only if the series 2 to the power n, a2 to the power n converges. Now let's look at this series 2 to the power n, a to the power n, a2 to the power n. So let bn is equal to 2 to the power n, a2 to the power n. So let's see how does our what is the behavior of this sequence bn. So this is just a, and in the definition of an, just replace n by 2 to the power n. So that will be 1 upon 2 to the power n log 2 to the power n to the power p, which is, this 2 to the power n gets cancelled out. This will be 1 upon n log 2, just by the properties of log. This will be 1 by n to the power p times some constant. Log 2 is a constant real number. So log 2 to the power p. Now summation bn, this is, we can take this log 2 to the power b outside because it is independent of n, and from 2 to infinity, summation n from 2 to infinity, 1 by n to the power p. Now we will be using the p series test. By p series test, we know that this series is convergent for p strictly greater than 1 and divergent for p less than equal to 1. Just look back where we discuss the P series test. Now, by P series test, summation 1 upon n to the power p is convergent for p strictly greater than 1 and divergent for p less than equal to 1. That means summation bn converges for p strictly greater than 1 and diverges for p less than equal to 1, which will give us that an, because by Cauchy condensation test we know that an summation an converges if and only if summation bn converges, and summation bn is converging for p greater than 1 only. So this implies summation an converges for p strictly greater than 1. Now next case would be p less than 0. Case 2, p strictly less than 0. So in this case, what will be our an? So for any negative real number, I can write it as some minus k. For some positive real number, we can write p to be equal to minus k. So here, summation n from 2 to infinity an will be summation n from 2 to infinity. That was 1 upon n log n to the power p, where p is minus k. So this eventually goes to the numerator. This is summation n from 2 to infinity log n to the power k upon n. So I can write it as log 2 to the power k upon 2. We'll see why I did this. Log n to the power 3, sorry, k upon n. Now since log n is greater than equal to 1 for all n greater than equal to 3, we know that where this log is actually the natural log. So log n is always greater than equal to 1 for all n greater than equal to 3. That gives us log n to the power k is again greater than equal to 1, just divided by n. This happens for all n greater than equal to 3. Now this tells us that an, that summation n from 2 to infinity, which was log 2 to the power k upon 2 plus summation n from 3 to infinity log n to the power k upon n. This is greater than equal to log 2 to the power k upon 2 plus summation n from 3 to infinity 1 by n. Now we know that summation summation 1 by n is a divergent series. So if I write it as, suppose if I define the sequence bn to be log 2 to the whole to the power k upon 2 for n equals to 2, and this is equal to 1 by n for n equals to 3, n greater than equal to 3. So from here we get summation n from 2 to infinity an, this is greater than equal to summation bn n from 2 to infinity. Now this is a divergent term since summation a 1 by n is divergent. Summation an is something which is greater than infinity, that will eventually be infinity also again. That means summation an diverges. Therefore, eventually the series was convergent only for p greater than 1. Only for p strictly greater than 1. For p less than equal to 1, in fact for p negative also, the series turns out to be divergent. I hope this was clear how we used the Cauchy condensation test, then we used the comparison test, sorry, p series test, and also we showed how for case p negative, the terms will eventually be going to, the sum will go to infinity. If you have any doubt at any step, please let me know. I would like you to try the second part yourself. Kind of eventually you'll be using the same things again. You'll be have in the setup of Cauchy condensation test, and then yeah, I would like you to try it yourself. How the things are happening for again for different values of x. You'll have to see for the case of x positive, x negative in this second part. Please try it yourself. It will be a good practice. Okay, so yeah, we still have time. We can discuss one more problem. Test the convergence or divergence of the following series. Mm, Summation n from 1 to infinity log n upon n to the power 3 by 2. So in order to see the convergence of this series, we need to know firstly that the sequence, I will just write it in some other color, recall. You can check this using basic L'Hopital rule also, that limit n tending to infinity log n upon n to the power alpha, this goes to 0 for every alpha positive. So I'll be using that. This implies, by the definition of limit of a sequence, for any epsilon positive, there exists a natural number n such that mod log n upon n to the power alpha minus 0, this will be less than epsilon for all n greater than equal to capital N. Now, if I take this epsilon to be 1, I will be able to get some natural number which obviously depends on epsilon. So, taking epsilon equal to 1, we will get, I'll call it n1, some n1 in n, such that mod log n upon n to the power alpha, this will be strictly less than 1 for all n greater than equal to n1. Now, since log n is always positive, so I can remove this modulus. So eventually I'll get log n strictly less than n to the power alpha for all n greater than equal to n1. And in fact, it will depend on alpha also. I'll write it as n1 comma alpha. Now above we have n to the power 3 by 2. So for that, I basically want to show that log n upon n to the power 3 by 2 is less than 1 upon n to the power p for some p strictly greater than 1. Because in that case, the series corresponding to this will be the p series, and since p is greater than 1 by a p series test, this will be convergent. Now, write it in some other color. In order to prove the convergence of summation log n upon n to the power 3 by 2, we would like to show that the sequence an, which is log n by n to the power 3 by 2, is less than 1 by n to the power p for some p strictly greater than 1, or log n is strictly less than n to the power 3 by 2 minus p for some p strictly greater than 1. Okay. So let's see how this p greater than 1 will get. And we have log n strictly less than n to the power alpha for all n greater than equal to n1 alpha. That means we want n to the power alpha to be less than n to the power 3 by 2 minus p for some p greater than 1. Now if I take this alpha to be 1 by 3, so in that case I will get log n upon n to the power 3 by 2 will be less than n to the power 1 by 3 for all n greater than equal to n 1 comma alpha was 1 by 3. Sorry. Yeah, this here we'll have 3 by 2 as well. Now this will be 1 upon n to the power 3 by 2 minus 1 by 3 will eventually be 7 by 6. Now since 7 by 6 is greater than 1, this implies summation 1 by n to the power 7 by 6 is convergent. That would imply, and this happens by p series test, and hence by comparison test, summation log n upon n to the power 3 by 2 will be 5. I would like you to go through this solution once again, and using exactly the same procedure, you can prove the second part yourself. Just try it yourself. Summation n from 1 to infinity log n square upon n to the power 3 by 2. You'll just have to look for some alpha such that again using the same thing. Uh, yeah, this happens. Hmm. So that you can follow exactly the same thing as done in the above part to prove that the series will be convergent. Yeah. If you have any doubt in this part A, please let me know because using that only you can be able to do part B. And if you think that these things are very complicated, please don't get worried because yeah, these things take time. It's not that easy to understand all these things. That is why I'm asking you to just go back and look at all the things again. I'll try to upload the video as soon as possible. And yeah, please go through it once again. In fact, 2 3 times. Write, make a habit of writing your own notes so that yeah, whenever you write yourself using your hand in your notebook, you eventually gets the things. Okay, if you have any doubt, please ask, or else we can finish this session. And also if you want something specific to be discussed in like next lecture so that I can prepare that. Okay, then if there is no doubt, let's finish this session. We'll meet next Saturday. Thank you.